Hi, here's the lecture for Chapter 9. There's only 11 chapters, so hey, we're getting down the end. We're now moving up the OSI layer. We've gone past the IP level. Now we're on to the fourth layer, the transport layer. So let's get right into it. So the objectives here is we're going to talk about the different transport layer protocols. Basically, the two main ones is TCP and UDP. So we'll talk about their purpose, and then we'll get into each of the different protocols. We have a little section on TCP, a little bit on UDP, compare the different, how they operate differently, explain how TCP establishes and terminates processes, its protocol data unit, how UDP establishes communication, and then determine how do I know if I want to use TCP or UDP, which ones are best suited for which application. So that's kind of what we're going to be. So let's talk about the overarching description of transport layer protocols. Now, what is the role of the transport layer? It's responsible for establishing temporary communication between applications and then making sure the data gets there. The link between, it's kind of the last link between both the application itself and the network below it. So it's kind of like I'm not in the hardware, I'm not in any addressing, but I am going to be concerned about which application am I talking to. Because most of us have, when you're online with the internet, how many applications you got running? One? No, most of us have 4, 5, 6 applications running at the same time. Well, the transport layer's responsibility is to keep track of all those communications, because I only have one network interface. If you got a wireless interface, you may have two, but you basically got one connection to the internet, but I could have 5 applications running, and it's the transport layer to say, how do I keep track? I don't want to be in Facebook and get it, something from Twitter appearing in the middle of it. So that's the job of the transport layer, is keeping track of all those individual applications and sessions. So it keeps track of conversations with each application. It also takes the data, because remember, coming down from the application, I can send in War and Peace, and we know based on frame sizes that there are limitations as to how much data I can send in one packet. So what happens, the transport layer's role is to segment, divide the data, and put a sequence number in there so we can put it back together when it gets passed up to the application. So you got tracking the conversations, segmenting the data you're going to send, and of course it has to identify, if you have multiple applications running, who's going to receive what information from who. So one of the things that, because you only have usually one network interface, and I'm breaking this data into several different applications, I'm going to do what they call multiplex. I'm going to interleave different applications' data on the same link. Not everyone is going to get access to the data all the time, to that network interface all the time. So it's got to make choices as to who gets access to the network, so to speak. So I'm dividing that smaller chunks. I'm interleaving them together to make sure that, and keeping track of that. So the segmentation allows me to multiplex, which means put multiple things in the same path. So now the transport layer. Now it says reliability. Well, TCP and UDP, they're two different protocols. But when Cisco says reliability, it isn't a matter of whether it's good or bad. It's, do I want to ensure, if I want a reliable network, I want to make sure that the data gets through. So I'm going to take total control over, have I received everything? And that's kind of what TCP does. TCP says, I'm going to make sure that everything you're sending is received, acknowledged, and if it isn't, I'm going to tell somebody to retransmit. UDP says, I really don't care I want to let somebody else, I'll let the application, I'll let somebody else worry about sending the data and that it got received. Now, it's got less data, less overhead, it's faster. So you can kind of guess, if it's faster, which type of application do you think would use UDP? Streaming video, maybe? Because how many times have you watched digital TV and all of a sudden you see those little squares on the scene, or you get the little circle saying, hey, I'm trying to upload data? Well, guess what? UDP is just that I'm just pumping data out as fast as it gets. If it gets corrupted, it gets corrupted. If it gets slowed, it gets slowed. It does not care. It's going to let somebody else worry about making sure that stuff takes place. So that's kind of the definition of reliability. Now let's get into TCP. Now TCP, it says I've got all these broken down packets, this segment. I'm going to take the data that's coming from the application and I'm going to divide it. I'm going to divide it into segments. And then each segment is going to get identified a number. It's going to get some kind of it's going to get an identifier so that it can be put back together on the backside. Because we know that a packet may not follow the same route from destination point A to point B. So I have to identify it. TCP is making sure that takes place. So it doesn't really make any difference because once it gets through my network and hits the internet, I have no clue how the segments go through. So I've got to segment it and making sure that each packet is tracked. And if I'm missing a packet, if I'm sending 5 segments to you and segment 3 is missing, I want to make sure that I tell somebody to retransmit, and that's that reliability. So TCP is going to ask for messages to be resent. Now, TCP's got 3 major responsibilities. One is numbering and tracking the data segments, acknowledging the data has been received, and then retransmitting anything that hasn't been acknowledged over a certain period of time. So that's really what TCP does. Now, those are the major functions. So I number and track, I acknowledge the received data, and retransmit anything that hasn't been acknowledged based on some time period. Now, UDP, on the other hand, less overhead. So that means it reduces the possibility of delays. And what it uses, it says unreliable, but it's really just trying to make that best effort. It's just trying to go out there and say, hey, I want to just try to get out there, get access to the internet, and send the data the best way I can. There's no acknowledgement. There's nothing going on. So it's pretty much like, hey, it says a non-registered letter that, hey, I'm just putting an envelope in the mail, and we hope it gets there, and we assume it gets there, but we really don't know. But if you wanted to know, what did you do? You actually register the letter and says, okay, somebody's got to sign for it on the other end. Somebody's got to acknowledge the receipt of it. That's reliable. That's TCP's job. UDP doesn't really care. Now, the question is which applications do you choose? TCP, they're very good about, you want to use them for databases, web browsers, email addresses. UDP, streaming video. Some email that just says, I'm stored it someplace else, I don't care. So if it doesn't get through, I still have it. But usually you'll see it more in UDP as far as streaming video, and TCP, it's web servers, it's email addresses, it's database access. So voice and video, UDP, data specifically goes TCP. Now, TCP, because it is a reliable network, I've got to make sure that I've established a connection or established a session. And what it tries to do is says, I'm establishing a session. It does it in 3 steps. So the major features of UDP is I establish a session. I make sure the delivery's reliable. I make sure that once it goes to the application, I've got the same order. So if something's missing, I'm asking for retransmission, and then once I get everything, I put it all back in the same sequence and then send it up the application. And the other thing I worry about is flow control. Am I receiving too much data at one time? So slow it down, speed it up, whichever way. So it's trying to manage the whole session to make sure things are going well. Now, the header, knowing you've got so much more things that could go right or wrong with a data, the header is definitely larger. So the biggest secrets, I've got a port number, which is which application am I talking to, the source and destination applications, sequence number, acknowledgement number, and then you've got windows as far as how much am I going to, number of bytes that can be accepted at one time. How do I know if things get through correctly or not? That's with the checksum. So I've got the sequence number that's used for data assembly. The acknowledgement says, hey, have I received, which acknowledgement number says, hi, which data has been received and ready for the next byte. So I'm going to kind of say, I'm ready to send this. You sent me bucket 2. I'm expecting bucket 3 next time. So that's what that acknowledgement number kind of gives you, is that information. Control bits and how to control the application for the segment. The window size is how many bytes can I take at one time. And then checksum, like I said, is for that error. Did I get a clean packet? UDP, on the other hand, says, hey, I'm not going to, here's the data, it's restructured, I'm going to send it. I don't care if segments are lost, they're not reset, there's no established session, establishment session. So I don't inform the user that something failed. So it really does not care, and that's why you see it in voice and video. Voice, because the mind can fill in a lot of the gaps if data's missing, and streaming video is, well, if you get a little bit of corrupted, your mind also can kind of put together, if I'm just missing one green leaf out of a tree, you can still tell it's a tree. So it's easy enough to augment that difference. And with that, the packet, the header size is a whole lot smaller, and all it is length, source and destination ports, and the length and checksum. So it's not a lot of application, a lot of data, a lot of overhead. Now, there are definitely some special ports out there for different applications. So there's separate applications that the internet bodies have assigned port numbers to make sure that they're locked in. And what you're seeing here is I've got 3 different ports. You got email, which is port 110, HTML or your web browsing at 80, and your internet chats are in port 231 or 531. Sorry. So these things are always the same, no matter what. Now, there's a whole lot of other ports out there, but these are some of the biggies that you use a lot. And anytime you send a text, an email, hit a web page, you're going to see that when you do your Wireshark exercises in this chapter, that you'll see those same ports now. Now, here's a little bit more data about each one of those. So what do I have? I got a source port, a destination port. So you got different software that's being run on your email. It's a POP3, HTTP. When you look at a web page, what do you see? When you get a URL, you see an HTTPS or an HTTP. Now, HTTPS is a secured HTTP, and you would notice that port number will change with that. So knowing that, here I've got a source port, a destination port. I'm going through. Now, to keep these things together, you've got to have 2 different things. I've got a source port, I got a destination port, but when I put the IP address and the port together, because that's the unique identifier to say, I want to get this data to a particular application on your PC, I've got to pair up those 2 bits of information. I've got to pair up the port and the IP address, and when that's done, they call that a socket. And you can see that some examples, they'll separate that column, that socket number, with a colon. So that way, every IP address, so for your network interface card, always has one address, and it's got a port for the application. And that way I can have multiple applications running at the same time. I got the same IP address, but I'll have different port numbers to make them unique. Now, there are definitely there's a whole large range of port numbers, and there's three major categories of port numbers. One, if the range between 0 and 1023, they're well-known port numbers. Well-known port numbers, those are reserved for services and application. You saw a couple of examples, HTTP, email, texting. Those numbers are assigned. Those are well-known ports, so they're reserved for those applications and never can't be used by anybody else. Then you've got a range between 1024 and 49151 are registered ports. These ports are assigned, but they're assigned based on requests that I have a specific application or process that I want to make sure I have a port number. So there's a range that allows me to request one, have the IANA assign me a port number, and go on. And then everybody in my application will go to that port. And then anything above 49152, they're private, they're dynamic, they change. And every time you do a text, or you do a different application, you're going to get a different port number. And every time it opens and closes, you're going to get something different. Especially on the sending, and I mean, my destination is going to be a well-known port number if I'm sending an email. But what I'm sending, I don't care on my computer what it is, but I do care where it's going. So I'm going to probably use a well-known on the destination, but my source is going to get a private port number, which I really don't care. And those will change every single time. Now, this is a table you want to keep handy. It's got some well-known port numbers, so you're going to need to know the port number, which protocol, is it TCP or UDP, and then what the application is. So you're going to make sure you can keep this table in handy, because you're going to see it on the test or in the homework assignments and stuff. So you're going to have to know the port number, the protocol, what application, and then what the acronym is. Now, there's a couple of interesting ones here, like you're seeing here. This FTP has two well-known port numbers. Now, one is for data, port 20 is for data, port 21 is for control. So just keep in mind, some of these are duplicate. I shouldn't say duplicate, they're actually split, in this case, for different features. So I would bookmark this table, find it in your, print it, keep it handy, because you're going to see it and need it. Now there's a command on your PC called netstat that allows you to see protocol address, what's the external address, what the port numbers are. And here there's an HTTP, but we know that's what? That's a known port, that's port 80. So the colon should give you a key that I'm using the internet web browser to do this. So it just kind of keeps track of all your connections that your PC has. Now let's get a little bit more into TCP and UDP. Now, TCP server processes basically says what? I've got request destination ports, sending clients, I've got requesting sort ports. So I've got a lot of activity that's going on here going up. So if I'm going to respond to destinations or resource ports, just keep in mind that every now and then you're going to get a destination port from your PC to a well-known port. So go through. Now, I'm less concerned about this process, but I am concerned a lot about this establishment process. It's a three-step process, a three-way handoff or handshake process. So the step one is the client makes requests for a session with a server. So it sends an SYN, a sync command. The receiver, the server says, I've acknowledged that you've made a request for a connection. And by the way, you're going to start your sequence number with 300. I'm expecting an acquisition. The next packet I'm expecting is packet 121, and my control values, flags are sync and acknowledgement. So it actually says, I'm acknowledging the request for the sync, and here's my terms for negotiation. Then the client says, okay, I'm agreeing to those terms, and acknowledges the terms. So and then it also sends back, here's my sequence number. So I'm sending you the sequence because you told me in the previous packet I received, you sent, was you're expecting acknowledgement 101. So I make sure my sequence number is 101. Well, I think they've got this flipped. It should be sequence number should have been 301. Acknowledgement should have been 101. And then it's an acknowledgement. So it's three-way handoff. So I'm asking for a session to be established. I'm acknowledging that request, giving you some starting parameters, and then you send the acknowledgement with the appropriate feedback. Now, termination, it goes through a four-step process, but it basically says, hey, I'm finished. You've received the finish. I've acknowledged that finish. But then it says, it acknowledged it. In a separate message, it says, I'm sending the finished. It says the finish has been received, and I acknowledge that finish command. So it's kind of a four-step process. So you got the sender saying, I'm closing this application down. The receiver sends two packets back, one acknowledging the request, and two saying, hey, shut everything down. And then you send an acknowledgement that says, thank you very much, terminating the conversations, and both sessions are done. Now, your three-way handshake, we just went through that process, but there are 6 control bits in TCP, and you see those right down here as far as the ones we mostly use. You got acknowledgement, sync, and finish, but there are a couple others, and you may be asked to cover those. Now, there's a great video on Neticat as far as the three-way handshake. I would take a look at it. You're going to do a Wireshark lab on TCP three-way handshake. So you're just going to observe. So you have to find a PC. It can be a wireless or wired application, but that's what you're going to be looking at. Now, TCP reliability. Now remember, we got sequence numbers. They're assigned in a certain sequence, and TCP says, hey, I'm going to represent each byte in the TCP segment. So during initial setup, there's going to be an initial sequence number. I'm going to tell you what that first sequence number is going to be and what the starting value is going to be. I'm also going to tell you how big of a packet it's going to be, and then that way, if something's missing, I can ask for those destinations, because this ends up being the key here is I don't know which route they're going to take. And if this router goes down, I may delay that or lose the information altogether. So then I got to inform the sender to retransmit. Once I get it, I put it back in order. So I'll go through. There's a good video on TCP on sequence number acknowledgement, because I can tell you exactly how many bytes I'm going to send, what acknowledgement I'm going to expend, what I expect them to be. Are there some packets I can ignore? Don't acknowledge every packet, but acknowledge every 5th one. So it's a pretty good video that you want to take a look at. Same thing with the video on loss and retransmission. I would highly recommend you take a look at that. Because this kind of gives you enough to, because all that deals with flow control and basically says, hey, I'm going to, when we set up the session here in this example here, we want 1460 bytes of data in each segment. So, but the window size says I've agreed that the window size is going to be 10,000. So I'm going to, before I acknowledge anything, I can send a bunch of packets and then only acknowledge the next, when it gets to 10,000. So it's kind of an easy way to, so I can minimize that overhead, So just an idea that you can identify the maximum segment size, you can identify the window size for acknowledgement. That way I can send, okay, now it's time to acknowledge, send data. So as I get to certain numbers, then I can go through. Now, the other thing TCP does is flow control or congestion avoidance. Congestion says, hey, I've just noticed, I've got lost segments. So then I got to retransmit. So to avoid and control that congestion, there are several things that TCP does. It's got some timers and a few algorithms that are pretty complicated, but just know that there are tools that TCP uses. I mean, it may change reduce the number of bytes that are being sent. It may change how often you're going to give a reply. Now, UDP, on the other hand, it's not connection oriented, so I don't care. I don't set up, there's no establishment, there's no session establishment. I'm going to there's no flow control, data gets lost, nobody cares. So it's definitely interesting. So basically what? UDP reassembles the data. So it still breaks it up, but it doesn't care that it came up out of sequence. It doesn't care if a packet, a segment's missing. So it's expecting the application to do something with it. So UDP just says, hey, I don't care. I'm just sending it. You get it and go through. Now, there is, if you want, in some cases for security purposes, you can have a remote authentication when you dial into a server or a service. And that's called a Radius server. And it basically just says, I'm making a request. It goes to the server then says, if you got the right password, login and password, then I will provide the appropriate destination ports needed. So just know that there is a way to secure UDP processes. This just gives you an example of using a UDP, the Radius service, to kind of give you a little bit of control, making sure that who you're sending it to is who they say they are. Continuation of that. You will do a quick UDP DNS capture session. And let's look at some of the applications and what uses. Now, TCP, there are a few applications, and we mentioned some of those. So in my mind, if you're trying to control data, you're going to use TCP, and that's what you see here. I've got, I'm trying to use my web server. I'm going to do a file transport. I've got email. I'm trying to connect into a device. All of these would be candidates for TCP because I want to make sure data doesn't get lost and it's correct. Now, UDP, on the other hand, because it uses, the type of applications that UDP uses, video, multimedia, our ping command, it's just simple requests and replies, and let the application deal with it. So here you've got in DHCP, DNS, different email protocols, transfer protocols, voice, TV. So when I'm not worried about the reliability of the data, I go through. Of course, you're going to get a chance to do a capture with TCP and UDP, and it should be fine. So hopefully this chapter should be easier than a lot of others, even though you got a lot of different data and port numbers and stuff. But for the most part, you understand a little bit how transport protocols work and the different types and how they support end-to-end communication. So hopefully that helps. And if you have any questions, give me a call. Thank you.